Part B. Well, we have a Maclaurin series now in that general term, so whoops. Now we do. We're going to determine the interval of convergence using that general term, which means that hopefully, as you know, well, maybe you're watching this as you're learning this concept and not just reviewing, we're going to do the ratio test, which means we're going to take the limit as n approaches infinity of a sub n plus 1 over a sub n, because this is basically sort of a, well, power series, and we're going to make sure then that that ratio is less than 1, so that power series converges. And then we're going to test the endpoints of this interval of convergence, because this is just going to give us, well, kind of initially the radius of convergence, and then we'll know what the open interval is for the interval of convergence. So we have a sub n plus 1, which means that we're going to just look at this general term, and everywhere we see an n, replace it with an n, so n plus 1. So we have negative 1 to the n plus 1 plus 1, which is n plus 2. We have times x to the n plus 1 plus 1, which is n plus 2, over n plus 1 as a factor, times 3 to the n plus 1. Now I'm going to go ahead and we have that a sub n plus 1 term now divided by a sub n. I'm going to flip that up and change that to a multiplication of the reciprocal just to save some space on the chalkboard. So we're going to multiply by, not divide by a sub n term, but multiply by the reciprocal of the a sub n term. So that means we're going to multiply by n times 3 to the n power over negative 1 to the n plus 1 times x to the n plus 1. And we're going to make sure that that limit stays less than 1. Okay, so is there anything we can cancel out? Well, here we have n plus 1 bases of negative 1, and in the numerator over here we just simply have one more. Well, I'm going to show this cancellation, but ultimately we have absolute value symbols, so that negative 1 is going to cancel out anyway. In the numerator of our first factor, we have n plus 2 bases of x, and here we have n plus 1 bases of x. So here we have one more base of x than we have in this denominator, so that's going to cancel out. We have n bases of 3 in the numerator, and we have n plus 1 bases of 3 in this denominator. So as these cancel out, we're going to have one base of 3, one factor of 3 left in that denominator, and nothing's going to cancel with this n over n plus 1. So we're looking at the limit as n approaches infinity. They did tell us to show our work. This might be a little slight overkill for some of us, but I think it's good. Negative what? N times x over n plus 1 times 3. Again, for the ratio test, we need to make sure the limit as n approaches infinity of this is equal to or less than 1. Now, the absolute values are going to basically just take care of this negative for us. And remember, we're letting n approach infinity, not x. So you're looking at just this n over n plus 1. And we don't need to show like L'Hopital's rule or some kind of process to show that the limit of basically n over n plus 1 is equal to 1. They're not expecting that much work to be shown. We're just looking now at the absolute value of x over 3 is less than 1, which means that if we multiply both sides by 3, just as a review, we could look at this expression and we could see the center of convergence, which we don't really need to because we're told that it's a Maclaurin series, which is basically just a special type of Taylor series where the center of convergence is equal to 0. But we could see that this is the absolute value of x minus 0, which means that the center of convergence is 0. And then that absolute value of this binomial that has a coefficient of on the x of 1, see, I got rid of the coefficient of 1/3, minus 0 is less than 3. When you have it in this x minus c, absolute value of that is less than, basically you're looking at r, your radius of convergence. So our I can't call it an interval of convergence yet because we haven't tested the endpoints, but we have so far a open interval of -3 to 3. Now that's not an interval of convergence, but it's like we're almost there. Now all we have to do is test the endpoints. We have a center of convergence of 0 and a radius of convergence of 3. So now that we have this open interval that is the beginning of us developing the final answer of what our interval of convergence is, we need to test the endpoints. Okay, so we're going to do that by using this general term and write not this whole Maclaurin series, but just the series in terms of sigma notation. So with the endpoint of x equals -3, we have the series where n starts at 1 and goes to infinity, which I should be including that, correct? Yes, okay. We have, using again this general term, we've got -1 to the n plus 1 power times, now not x because we're replacing it with -3, so -3 to the n plus 1 power over n times 3 to the n. And all you have to do is show the work as you start to determine whether this series converges or diverges so that you know whether to include the endpoint of -3 or not. And I'm going to show a lot of work just to make sure that I don't miss the question and, well, you understand what I'm doing. So first thing I'm going to do is bring out this -1 as its own factor so we can see how it combines with this -1 to the n plus 1 power. When you multiply like bases, of course, we add the exponents. So rewriting that -3 to the n plus 1 power, we have, with the expansion now, -1 to the n plus 1 times -1 to the n plus 1 times 3 to the n plus 1. Multiplying these like bases, the two bases that have the value of -1, we have -1, n plus n is 2n, and 1 plus 1 is equal to 2. So we have this series where we have -1 to the 2n plus 2 times 3 to the n plus 1 power over n times 3 to the n power. This -1, its exponent is 2n. If you take a number and multiply it by 2, it's even. If you add 2, it's still even. And -1 to an even power is positive. So the -1 goes away. We have 3 to the n plus 1 in the numerator, and we have 3 to the n in the denominator. So the numerator has one more base, or factor of 3, if you will. So this is going to, the 3n in the denominator is going to cancel out with all but one of the 3's in the numerator. And now in our series notation, all we have left is 3 over n. And I'm going to go ahead and, just to make sure it's perfectly clear, we're going to pull this factor of 3 out in front of the sigma notation so that we can see that we have 3 times the summation where n starts at 1 and goes to infinity of 1 over n. Well, that series, basically the series of 1 over n, is a harmonic series which diverges. So this is harmonic. Give a reason, please. Harmonic series diverge. So for the purpose of this problem, finding the interval of convergence, at least in terms of the interval of convergence, x cannot be equal to -3. Okay, so this parentheses on the left of -3 is going to stay. Now let's test x is equal to +3 and see if this is going to be an open interval or closed interval on our interval of convergence. One more time, write out that series notation, that sigma notation, or the series with sigma notation, Maclaurin series with sigma notation. So we have the summation where n starts at 1, goes to infinity, one more time, of -1 to the n plus 1 power times 3 to the n plus 1 over n times 3 to the n. Problems like this is really why in Chapter 9 with all of your interval of convergence tests is for this final step of finding your Taylor and Maclaurin series, testing the endpoints. So we have 3 to the n plus 1 over 3 to the n. So in the denominator, all of those factors of 3 are going to cancel out, leaving you with just one factor of 3 in the numerator, and there is nothing to take care of that negative 1 to the n plus 1. So this is, again, moving that 3 out front. Just to make this abundantly clear, we have 3 times the summation, where n starts at 1 and goes to infinity, of negative 1 to the n plus 1 power over n. And that is a alternating harmonic series which converges. Thus, 3 can be into our interval of convergence, and the interval of convergence starts with the open, it's open on the left side, so from negative 3 open to 3 closed, or you can say that negative 3 is less than x, which is less than or equal to 3, is our interval of convergence for our series negative 1 to the n plus 1 power of x to the n plus 1 over 3 times 3 to the n. All right, that is part B. Part C coming up right now.